Okay, so in this short video I will show you how to easily make a second level analysis in SPM. You can see here that MATLAB is already open. We're just now going to add SPM to the path. So I'm here working on a Linux machine. So for you it will be a Windows computer, and you will also use SPM 12 instead of SPM 8. So that's just now what I'm going to use, but it doesn't really matter for the example. Okay, then we open SPM. So, and then here in the menu window, we can just choose here specify second level. And a typical batch editor opens, where we have the possibility to input some different things. So first of all, our analysis will be stored in a directory. So here I would recommend that you always make a new directory. I already created one here for our example analysis. It's just an empty directory where the SPM mat file for the second level model will be stored, and also the contrasts that we will create. And yeah, since there are a bunch of files that belong together, I will always recommend to make a new directory with a name that also makes sense. And then here under design, you can choose different models for your second level that you would like to use. So for example, a two-sample t-test, independent sample t-test, or paired t-test, multiple regression, or the full factorial design. So this is just now a display error here in Linux, but normally this should look fine. For this example here, I'm just going to do one sample t-test. There's one possibility here for an input. So I'll just put here in some contrast images that are somewhere no, that's not the correct one. Model contrast encoding, for example, and then we look at, so this is from old memory data that I have here, so we will just look at the contrasts remembered or forgotten. So what brain activation changes do we find at encoding for items that will be later remembered as compared to items that will be later forgotten? So these are 34 participants, and yeah, I of course need to input also the directory here. So that is in the Teva directory, right here. One sample t-test, so the empty directory. If it's not empty and you want to run the model, then of course SPM will always give you also an error warning saying, are you really sure that you want to override it? So there's an extra check implemented so that you don't override any data accidentally. This is actually, for the one sample t-test, this case here is very simple. This is everything that I would put in. And all these other things here I would just leave as they are set by default by SPM. So next, this is basically a design for our model, and we now want to estimate it. So we go here to SPM, Statistics, Model Estimation. We want to estimate the model that we just specified. So we say here we use this dependency option, which gives us here as a possibility to put in the previous step. Okay, and then we want to specify already a contrast. We can also do that later, but it's more convenient if you do this already now. We want to use again the SPM mat file that we just estimated, so from the previous one. So you can see here that theoretically you could also choose the SPM mat file from the first step. So this is also important, just that you can choose an option SPM doesn't mean that it is correct. What we want to use, of course, is the estimated SPM model from just one step before from the model estimation. And we want to make a new T contrast here. We could also use an F contrast, but here I just now want a T contrast, and I want to check which regions show significantly increased brain activation as compared to 0, so significantly above 0. That's why our contrast vector here is a 1, everything that is above 0. And you could now give it any name you want. So we could just say now positive contrast, for example, positive contrast. Or you could also name it a 1 or whatever you like. That doesn't really matter. Just something where you can then afterwards understand what you did. So we actually specified everything we need for our second level model. And this also means, so if everything is correctly defined in this model, then here this arrow here turns green, and we can run the analysis. So then here you see that something will happen in the command line, but also here you see the progress window, and this is basically what our second level design now looks like. This is very simple, it just has one column because it's just a one sample t-test. If we would look at the paired sample t-test or an independent sample t-test, we would have here a 2x2 matrix with the two conditions, the two groups that we want to compare. Okay, MATLAB already says that everything is done. So now we can check the results, and we do that here by clicking on results, and we can choose the model that we just ran. So we go to our table folder, table folder, run sample t-test, and here this SPA mat file, so that's the most important file, it contains all the settings that we just put into the batch file. And we look at the results by just opening the mat file. And we see here, so first of all, what always happens is that the contrast manager opens when you open SPA mat file, and you can see here all the contrasts that you defined already in the batch previously. So if we would not have entered anything before, then we could define here a new contrast and do the same here. So here positive contrast and give it a 1. In this case we did that already, so we just need to select it. And we do not want to apply any masking, so here we just say no, show us the whole brain. This is just the title that we just confirm with enter. So what I do is the first step, I just look at the results using an uncorrected threshold of just 0.001, so that's the SPM default. So I just say here no p-value adjustments, and also, yeah, exactly, so 0.001, that's the default. And I want to see all the voxels, so no clusters that are significant from a certain threshold or cutoff onwards, but just all the voxels we want to see. And that is not so much, but it looks okay. So this is of course one way to plot the results, the classic SPM way using this glass brain. I always want to look at it using a meaningful overlay, so I think I've somewhere already calculated a average structural scan from all the subjects, and this you can then exactly here average. So this average structural scan you can also find on the Teva shared folder, so you can just use that. You select that one, and then the activation is plotted onto this map. So this is a memory contrast with here the inferior temporal lobe, left and right, bilateral, looks very nice. Not so much hippocampus actually, but more the parahippocampal cortex, and the cortex, I would say. That shows increased activation at encoding for information that is later remembered as compared to forgotten. And also here the dorsolateral prefrontal cortex. Yeah, so this is a more useful way of just assessing your results compared to the glass brain. Let's see if our results are significant if we use the voxel-wise FWE correction. So we can just change the significance threshold by clicking on contrast, significance level, and change. FWE 0.05 and all the voxels. And we see here that there's if you correct for multiple comparisons, then the only thing that stays significant that remains is the left and right inferior temporal cortex. If we now say, okay, with memory, for example, so if we have small regions that we're interested in, the hippocampus or the parahippocampal cortex, then it's very likely that they do not survive this FWE whole brain correction. So an in-between level of correction is something that we would like. For example, cluster level correction. If we now go back to the 001 uncorrected threshold, so you always also can see here which threshold you're using by these values here. Then you can go into whole brain and you see all the activation levels here in the whole brain. What you then do to assess the number of voxels that a cluster needs to have in order to be significant is that you check here the cluster sizes and then the p-values that go with it. So for example, 41 is not significant anymore, 63 is significant. So I would say here now a cluster size of 63, for example, seems appropriate. So this is one way to assess the cluster size that is necessary for results to be significant using this cluster defining threshold. Another way is there are also scripts available online from Thomas Nichols from the University of Warwick. So he's the statistics person for fMRI. He developed some scripts that you can download so that you can automatically calculate the cluster size that is necessary, which is, I think, a more ideal way. But now for the table, we're just going to use the table here to look up these values. So I now choose the cluster size of 63 voxels, and I can set that this cluster defining or this cluster corrected threshold by going again here to contrast, significance level, and change. We do not want FWE, we want a 001 cluster defining threshold. This is also discussed in the Eklund paper. This is a threshold that is still fine. If you would go to 005 or less, then this is not acceptable anymore because there the probability is very high that you have a lot of false positive results. But here 001 is our cluster defining threshold, and our cluster size should be 63. So all the clusters that consist of 63 voxels or more are now significant. And these are the following ones, so that also cleans up the brain a little bit, looks also nicer. If you already used this overlay function once, then you can just use here overlays and previous section, just as I did before. So this is our final result, and what do we now want to do if we want to export this table here? So this is the table that that we would in a publication, in a written publication, we would want to report this table. But then of course it's difficult to understand which regions these coordinates belong to. So there are different toolboxes in SPM that you can use to check the coordinates. What I typically use is a script that you can also find in the software folder from the Teva shared directory. And the script, if you run it, if you have SPM open like this and you run the script, then it will output you a table just like that one here, but then with the labels of the regions printed next to it. And this is very useful. You can then just use it for your publications or your posters, or just understand what regions actually your activation blobs belong to. And the way you use the script is that you go back to the command line. So here we find a lot of stuff that just SPM prints to the command line. So you can also just clear it. It's fine. And then we have to add this, so just ignore this here, this is a screen error from Linux. So we have to add this script to the path so that MATLAB can find it. In my case here, this is located in home memory, is in MATLAB label peaks. So for you this will be then in the shared Teva folder, I think under the same name, label peak. So you just edit either by typing add path, or you can also say here set path and then select this directory. And then we run the script, label peaks, by typing the function name in the command line. and then you say x, small x, and uppercase letters SPM, comma, h, I think it's in uppercase, let's try, reg. So this is what you have to put in, and then press enter. And then what should happen is that you have here a, so this is the current directory where our results are stored, the contrast that we did, SPM mat file, and you can see here that there was a text file generated with the name of our contrast, statistics table positive contrast text. And this is the output of this file. So if we now go to, where do I have it? If we now go to, oops, to the folder where our results are stored, and we have here this text file in there. And you can see here, this is just the same, so up till here, this is just the same output as we already had using SPM, but then this, this script, which uses this specific atlas to look up these coordinates, then puts these region labels here next to it. So as I correctly already said, the left inferior temporal gyrus and the right inferior occipital gyrus. So in principle, you don't just look on the image also what the regions are, because this atlas here specifically only has gyri in it, so it gives it always very specific names. So also, for example, the medial prefrontal cortex, which is a very common region for memory, this one is also not an atlas, and then it will say you, like, give you a different name, for example, medial frontal gyrus instead. But then so when you're on a Windows computer, you just have this text file, and you can open Excel and read in this text file and then work with that for your publication. Okay, what is also important is that when you have SPM here open, we of course want to plot our results. So we want to have an image of our results for the poster, in our case, for example. So what we could just very simply do is we again plot it over the average structural scan that I already used before, like this one here, and we could just make a screenshot and copy paste this image then into PowerPoint, for example. This is one very easy and fast possibility. One other possibility is that you use MRICron or MRICro GL to create your activation images, your activation maps. But what is of course important is that you cannot just take this raw SPM T contrast here that we have here, because this is the not corrected one, so to say. But we want to have an activation image of the cluster corrected contrast that we have here, with 001 as a cluster defining threshold and the cluster extent of 63 voxels. So what we need to do here is that we save this cluster corrected image. We do that here by clicking onto Save, Threshold at SPM, and then we can give it a name that is contrast remembered forgotten P001 K63, cluster extent 63. That's just, I typically name my files like that so that I know afterwards. And what we then can do, so here's then the image that I just created using SPM.